Okay, let's dive right into this because today we are exploring a field built on a massive, almost impossible paradox. We're trying to guarantee safety in a world where, well, zero risk simply does not exist. We're talking about the invisible world of safety engineering. It's like this giant, fascinating puzzle that surrounds us every single day. We almost never think about it until something goes wrong, right? Yet it's the exact reason skyscrapers stand firm against hurricane force winds and why millions of cars navigate highways without constant catastrophe. Understanding how engineers negotiate this impossible paradox is absolutely going to change the way you look at the buildings you walk into, the software you rely on, and the everyday products you use. Welcome to The Explainer. To understand how engineers tackle this massive puzzle, we really have to start right at the foundation, the engineering code of ethics. Protecting the public isn't just a suggestion, and it's definitely not some lofty ideal. It is the absolute paramount duty of an engineer. Before an engineer even starts to worry about a project's budget, or how efficient it is, or making a consumer product look incredibly sleek, they carry this immense, fundamental responsibility to society to ensure their designs do not cause harm. When this mandate gets ignored, when cost or speed is prioritized over safety, the results are often these tragic structural failures that literally make global headlines. This ethical bedrock really establishes the immediate gravity of what it means to put any engineered design out into the real world. Now, what's really interesting about this is how we actually define the word safety. We typically define safety as the freedom from damage, injury, or risk. But in the engineering world, safety is actually a surprisingly slippery concept. It is somehow both highly precise and incredibly vague at the exact same time. It's precise because, evolutionarily speaking, our human instincts kick in instantly when we encounter a highly unsafe situation. We know a crumbling bridge is dangerous the absolute second we look at it. But it's inherently vague because codifying exactly what constitutes safe enough for a massive, complex population, that relies heavily on subjective human judgment. And as we all know, human judgment is rarely perfect. And that brings us directly to the other side of the coin. You fundamentally cannot build anything new without introducing risk. The two are permanently intertwined. You just can't talk about safety without talking about risk. Now, risk in an engineering context isn't just some vague, uneasy feeling. It's a calculation. It is the mathematical possibility of suffering harm or loss multiplied by the severity of that loss. Because safety has to be an integral part of any design, the engineer is locked in this constant, high-stakes battle with this exact calculation. Every new bridge suspension system, every autonomous driving algorithm, every automated factory machine, they all carry a very specific statistical possibility of failure. Think of it like this. Risk isn't a simple binary switch that's either on or off. It operates on a relentless sliding scale, and engineers must constantly gauge and manage this exact scale. They're looking at failure probabilities to determine if the potential for harm is incredibly low, sitting nice and safe in a mathematically acceptable zone, or if it's creeping up into high-risk, catastrophic territory. Managing this spectrum is the very essence of engineering design. It's a rigorous, nonstop balancing act between the amazing utility and innovation of a new product stacked up against the potential losses it might cause if the physics or the materials just happen to fail. Which inevitably leads every single engineer right to this monumental question. How safe is safe enough? I mean, if we know that zero risk is mathematically impossible, where exactly do we draw the line to say, yes, this product is ready for the public? This is the exact moment where the engineering discipline transitions away from hard math, stress tests, and physics, and dives headfirst into the highly subjective and honestly, often deeply flawed psychology of human perception. Because how the public actually feels about a risk dramatically alters what an engineer is permitted to design. Let's look at what actually influences our deeply irrational judgment of risk. And this brilliantly illustrates a fascinating quirk of human irrationality, agency. It shows how our perception shifts based entirely on our own sense of control. If we voluntarily choose to take a risk, our brains are remarkably okay with it. Think about driving a car. You are hurtling down a highway at 75 miles per hour, surrounded by thousands of pounds of metal and explosive fuel. Statistically, it's quite risky, but because you are holding the steering wheel, you feel totally safe. But take that exact same, or even a much lower, level of risk and make it involuntary, like flying in a commercial airplane where a pilot is entirely in control, and it terrifies millions of people. The math hasn't changed. But because the risk feels forced upon us without our direct control, our perception of the danger wildly spikes. Our brains also constantly weigh the duration of a risk, and it's often to our own detriment. We have a surprisingly high tolerance for short-term consequences, even if they're severely dangerous. For example, consider an industrial worker who decides to skip a tedious 5-minute safety harness check. They are literally risking a catastrophic, fatal fall, but the brain discounts that abstract future cost in favor of the immediate short-term convenience of just getting to work faster. Conversely, if a potential failure could cause a lasting, long-term inconvenience, like, say, a permanent detour on a daily commute because of a bridge repair, our perception of the design's danger or failure absolutely skyrockets. We are deeply, deeply biased by immediate ease versus enduring consequences. And then there's the timing of the risk itself. This is perhaps the most fascinating paradox of the whole shebang. If an action carries a severe risk, but the negative effects won't actually show up until decades later, we somehow process that as being much safer. We simply delay the worry. People will happily ignore the slow, delayed risk of inhaling trace chemical fumes over a 20-year career, yet they will be absolutely terrified of a sudden, dramatic boiler malfunction. Even if the delayed chemical exposure is mathematically deadlier in the long run, the immediate explosive threat always feels far more dangerous to the human brain in the moment. It is totally illogical, but it is exactly how human beings operate. So, the crucial point is this. When it comes to assessing risk, human logic is incredibly messy. We are biased by whether we choose the risk, how long the consequences last, and when those consequences actually hit us. Because our brains are so demonstrably bad at objective risk assessment, the engineer has to step in and act as the rational safeguard. They literally have to make the objective judgment call for a public that cannot reliably make it for themselves. This is exactly why your lawnmower has that annoying safety interlock that shuts the blade off the second you let go of the handle. The engineer knows for a fact that human convenience will always try to override logical safety. Now, engineers have to make these subjective, heavily calculated calls in highly chaotic, totally unpredictable real-world environments. Just picture a standard factory floor for a second. You don't just have one hazard. You've got massive moving machinery, pressurized hazardous chemicals, forklifts starting around blind corners, and hundreds of human workers all interacting simultaneously. The reality of engineering safety is acknowledging a really hard truth. Under these conditions, human error guarantees that accidents can and absolutely will happen. That is exactly why true accident prevention requires a highly comprehensive, multidisciplinary approach. You need mechanical, chemical, and industrial engineers all working together, rather than just relying on a single safety inspector walking around with a clipboard. Let's move to and see how this builds into actionable processes. So, how do engineers actually prevent these accidents in practice? Well, they use a rigorous risk management philosophy with one primary gold standard goal: designing out hazards. You see, the weakest way to deal with a hazard is to simply mitigate it, like slapping a bright yellow warning label next to an exposed spinning blade. The superior, real engineering solution is to completely redesign the machine's architecture so that human hands can physically never reach that spinning blade in the first place. The hazard is entirely eliminated from the design before it ever has the chance to cause an injury. It's a real game changer. But remember, engineers are human too, right? They still have to rely on their own subjective judgment to hunt down those invisible hazards. To prevent their own psychological biases from creeping in, they lean heavily on specific, objective analytical methods. Tools like line drawing and flowcharting are essentially the engineer's ultimate defense against human error. Imagine a chemical valve failing. A flowchart maps out the precise if this, then that scenario. If valve A fails, does the system safely vent the pressure, or does it cause a massive chain reaction explosion? By rigorously charting every single possible failure point and alternative solution, they strip the emotion out of the process, bringing cold, objective logic to a highly subjective task. Ultimately, all of this complex mathematical analysis and psychological balancing has to result in a concrete physical design. And for that design to be approved and released to the public, it must pass a strict two-step gauntlet. First, the absolute baseline. The design must strictly comply with all applicable laws, codes, and regulations. And honestly, that's often the easy part. It's just reading the rulebook. Step 2 is where the agonizing engineering work actually happens. Even if a design is perfectly legal, the engineer must prove that the remaining unavoidable risk is operating at an acceptable level, based on all those complex human factors we've just been discussing. Only when both steps are completely cleared is a design deemed ready for the world. So, we've seen the absolute ethical mandates, the mathematical risk meters, the analytical flowcharts, and the strict legal compliance laws. Yet, we've also seen just how completely subjective and irrational human perception really is. If the final call on what is safe enough for society ultimately comes down to a human engineer's judgment, are we ever truly free from risk? This ongoing tension between strict engineering rules and the messy, unpredictable reality of human nature is what makes the invisible world of safety engineering so incredibly vital to our everyday lives. Keep questioning the built world around you, and we'll see you in the next explainer.